Okay, so here's where we were last time. We were talking about partial derivatives. A super quick reminder, this book and most books start with partial derivatives. They are very useful. I'm not opposed to partial derivatives, but I do think they maybe get a little implicitly oversold as being fundamental. And I think that's really not the ideal sort of cornerstone point of view to have on derivatives. We're going to get to a better point of view on derivatives possibly today. But anyway, I'll come back and talk about that when we get there. But reminder about partial derivatives, they are really easy to motivate and really easy to compute. Recall our definition. We fix all the other variables and then take the derivative with respect to just whatever variable it says you want to take the partial with respect to. And of course we have interpretations of these things. Fixing all the other variables, in this case we're taking a y partial, so fixing x means we're taking a cross-section of the graph by the plane x equals a, which means that we're looking in the y direction. And it's easy to kind of get that backwards. Keep in mind when you're taking a y partial, it is x that is a constant. And it's because x is a constant that the plane kind of points, if you will, in the y direction. It's easy to get that confused. Of course, taking the derivative of the resulting cross-section is you're taking a derivative of a single variable function, and it's old news that that's the slope of that cross-section curve. So we get this interpretation right here of the y partial, and recall I left it as an exercise for y'all that I hope you'll give yourselves to make the similar argument about x partials. And it'll be a different picture and different details, of course, but it's extremely analogous to the argument that we just saw. So a good fill-in-the-blanks test for yourself to try. Okay, so now, reminder though, all of this, right, what are the geometric interpretations of partial derivatives? All of this that we were just talking about is in the context of graphs. And naturally, of course, it should depend on what kind of picture you're using. Are we looking at a graph to understand this function? Are we looking at level sets? What are we looking at here? Okay. So this is just the graph point of view. I'm going to underscore the graph part of these summaries. All right, this is how you understand partials on graphs. So totally separate question. What if you're looking at this picture, what I like to call the literal picture? Right? What does a partial derivative look like here? Okay, well, let's see here. If we're at this point and we want to compute a partial derivative apparently with respect to y, well, that means that we're going to hold the other variables constant. We're going to hold x and z constant. And, of course, holding x and z constant on this picture means that we're going to confine ourselves to this line where both x and z are constant. Right? And so, again, the upshot is that, well, that means that we're looking in the y direction. In particular, we're looking, as I move a certain amount, some differential amount dy in that y direction, I want to know, well, how much does the function change correspondingly? Right? And so, you might say that our output differential and our input differential are related. Oh, I should have, let's see here. Sorry. Our input differential and our output differential are related by way of this thing called the derivative. The derivative is the thing that you multiply by the input change to get the output change. Now, that's arguably it's not like I can again look at something really crisp like slope. Right? Graphs are really nice in that sense. The interpretation of the partial derivative is very crisp. Right? Here I have to view the partial derivative as a relationship between things that I have to pretend that I can see even though I can't. And so, yeah, it's a little less satisfying. But nevertheless, this communicates the question that we're asking and gives kind of an answer to that question as well. How we doing? Is everybody okay? All right. Okay. Okay, moving along. Level sets. So again, this is a very different picture. Right? And so please do not make the mistake of thinking that, okay, well, if you're at a given point and you want to compute a partial derivatives. Oh, partial derivatives are slopes. And so some students will make the mistake of thinking that whatever the slope of that line is, like it's the slope of the level set. And it's just not. It's just not, and it's not even close. So that's not what it is. Here we're going to have a very different picture, and keep in mind these level sets are representing constant values of the function, and I like to think about the metaphor of mountainsides. And if you have these different level sets, each one represents a different altitude there, right? And let's kind of think through. We already talked through last time about that, if you're trying to keep your hike reasonable, try not to cut straight through the contour lines, because that means it's going to be really steep, right? Said differently, the graph is going to be really steep. Said differently, the partial derivative is going to be large, right? So if you're going in the x direction on this picture, the partial derivative with respect to x, in other words, would be large, because, that's steep climbing. Right. Whereas, by comparison, if you're going in the y direction, golly, I mean, it takes you quite a bit further of a distance to cut through the same two contour lines, and so that's going to be relatively not so steep on the graph, and therefore partial derivative relatively small. Okay, so this is a very different picture. Now, something very unsatisfying about this picture is that I don't have a label here of how far altitude separated are those contour lines. And I don't have a scale on the x and y axes as I've drawn them. How much horizontal distance are we talking about for these, right? So it's kind of hard to get a precise understanding of what these partial derivatives look like in this picture. And that's that's the nature of the beast. The advantage here is that it's two-dimensional instead of three-dimensional. And you're going to lose some information. You're going to lose certain advantages. Hopefully not too surprising. But nevertheless, I think that's pretty believable. What do y'all think? Is everybody okay with this? Okay. Here's a different way to think about it. If I were to look at this input differential right there, when I move that distance, whatever the gain in altitude is, and I'm going to say maybe 200 feet because it's two contour lines, that's being divided by a small delta x, if you will. And so, it's large because you're dividing by small, right? By comparison, if I were to be going this other direction, gain the same 200 feet by going in the y direction, same 200 feet, right? But it took me greater horizontal distance to get there, so I'm dividing by a greater denominator, and so smaller. Same thing, different point of view. Everybody good? Okay. Alrighty. Okay, so now we're going to start doing some stuff with partial derivatives. I'm going to start, as the book does, with linear approximations. And I think there's a lot of really interesting ideas in here, and a lot of good stuff's going to come out of this. First thing I want to make sure everybody understands about linear approximations, this is very quick, but technically they're not linear. There is something related to them that is linear. But linear approximations, look at the formula here. It's not linear. 0 does not go to 0, right? It's one of the first things you learn about linear transformations in Math 218. But they are something called affine, whatever, who cares? But anyway, the point is there is a related object that we will soon see, as in later today, that is linear, and thus the name. Okay. Now, a proper treatment of linear approximations and where it's going to take us is pretty sophisticated and just a little bit beyond what we're going to do in Math 219. And again, disappointing for me. It's a wonderful conversation. There's some really beautiful ideas and closely connected but distinct concepts. But anyway, we don't have time for. Oh well. So I am going to have to, though, just to keep things honest, I'm going to start by saying we're going to talk about linear approximations on the assumption that they exist. There are some situations where, there's no such thing as a true linear approximation of a function. And we will talk about how to decide. We're going to talk about what that even means. And then furthermore, how to decide if it's a yay or a nay. A little bit later, again, hopefully later today, we'll see. But for the moment, let's just assume that they exist, assuming everything is nice, and then we'll come back and fill in that blank a little bit later. Okay, so I hope you all remember this formula right here. Right, that's an old Calc 1 formula. One of the first things you do with derivatives when you write down derivatives in single variable calculus. And this is the linear approximation formula. So what is it that makes this the linear approximation? And again, different ways that you can say it. Let me give you what I think is the anyway, one of my favorite ways to characterize this as the linear approximation, and that this is the unique degree 1 polynomial that has the same value as f and the same first derivative as f at the given point. So looking at some fixed point A, some given fixed point, right? This function, this thing that we call L, has the let's see, I've confused my colors here. Let's see, has the same value as f at the point A. If you plug in A in for x, you get f of A, right? So L of A is equal to f of A. This agrees with f at the point A, and furthermore, it has the same first derivative. So if you take the derivative of this function and then plug in x equals A, again, same value. So you might say that this is the unique first degree polynomial that mimics f at the point A. Same value, same derivative. All right, is that cool? Any questions about that? Everybody happy with this? Has everyone here either previously seen or now understands why this is a fair characterization of this thing? Okay. All right, so I'm going to use that as kind of a jumping off point for defining what we mean by a linear approximation of a multivariable function. So here we go, multivariable, right? Multivariable function, still real valued. Just for the moment, let's just think about real valued first. And I claim that this function right here has both of the above characteristics. It shares the same value as f at the point A, and it has all of the same multiple partial derivatives as f at the point A. All right, so let's talk through this and let me try to persuade you that this is true. Now, first, I'm going to label a few things in this formula. So, for one thing, on the right-hand side, there's some variables on the right-hand side, but there's a ton of constants. So, just to have it clear, that's a constant. This thing here is a constant. And slow down, you might say, wait a second, that's a partial derivative. Isn't that a function? No. This function has been evaluated at the point A. So, it came from a function, but it is a constant because we've already evaluated, before we get into plugging in x's, we have evaluated that partial derivative at A. So it is a constant. So that's a constant too, and likewise, that's a constant. And the point A itself, also constant. We've got a ton of constants in this function. Okay, so now that said, let's plug in x equals A into there, and if x is equal to A, well, this becomes 0, and that becomes 0. So all of these terms are 0, and sure enough, L of A is just f of A, as it's supposed to be. Everybody with me? Okay. Alrighty, but then let's see, what about the partial derivative? Let's ask this question, what is the partial of L with respect to x1? Okay, let's think through that partial derivative here. How would I compute that thing? Well, partial derivative with respect to x1 means that x1 is going to be my only remaining variable, meaning I set all of the other variables equal to constants. Yes?
Sorry, I just don't understand the notation of the bar.
Yeah, bar just means this says, okay, you got a function here, and the bar says, wait, stop, I'm going to evaluate that function at A. It's kind of an alternative to putting A in parentheses.
At x1 equals A?
I'm sorry, what?
At x1 equals A?
At x equals A. So this is a function of all the variables, right? Now, when you're computing it, you treat the other variables as constants, right? But once you've taken that partial derivative, it remains that all the other variables are still in there, right? So this is a function of x1 through xn. And what this says is that I'm going to plug in that the x vector, all of its coordinates are that A vector, all of its coordinates. Okay. Is that everybody happy? Okay. All right. Okay, yeah, so let's see here. So we're going to compute this thing here. What is that partial derivative? We're going to hold all the variables constant except for x1, which means that I further annotate my picture. x1 is the only variable, so that stays a variable, right? But all the other coordinates of x, like this one here, xn, constant now, for the purposes of taking the partial derivative. Okay, well that means, if you think about it, that all of the terms beyond the first one, all constants, right? That's a constant, that's now a constant, and that always was a constant. So what happens when you take derivatives of a bunch of terms that are 100% constant? Well, they go away, right? So once we take the derivative, this all just disappears. So what does remain is, the only thing that's got any function to it at all is, I have a constant times x1, and when you take the derivative of a constant times x1, the derivative is that constant. And so, as desired, we get the right answer. Everybody see how that argument goes? Now again, you can repeat this for all the other variables. So I just did this for just x1. Y'all can fill in the blanks. Again, this is a healthy exercise, right? But fill in the blanks and persuade yourselves that all these other partials work as expected too. Okay. All right. So this is the unique degree 1 polynomial that satisfies our requirements about values and derivatives. So this is what we call our linear approximation. Okay. All right. Now we're going to rewrite this a little bit. Convenience of notation is to notice that all of this stuff right here is structured just like a dot product. And furthermore, the part of the dot product, if you will, kind of the second factor in each of these terms, that part of the dot product, those are literally the coordinates of x minus a. Right, so what I've got in blue there structurally is apparently it's something dot the x minus a vector. And the x minus a vector, this is a pretty natural thing to talk about. And that suggests that whatever we're dotting it with, and so, the vector whose coordinates are those partial derivatives, that thing must be pretty natural because it's the thing that you dot with x minus a to do most of the work in that above formula. So we give this a name. This is called the gradient vector. And rewriting the gradient vector, rewriting the above formula in terms of the gradient vector. And so what I've got in blue up there turns into what I've got in blue down here, much more compact, right? Written as a dot product. It's not just that it's compact. Dot products contain information, right? Understanding this formula as a dot product means we understand more fundamentally what's really happening there, right? So this is a big win to rewrite it as such. And in doing so, we have this new thing called the gradient that we're going to do a bunch of stuff with. Okay, so now the linear approximation. Instead of having to remember this great big long thing, our linear approximation just looks like that. What do you think? Everybody happy? All right, now before I show you an example, let me just, there's an eyebrow raiser that I think is worth noticing, and I guess I'll have to zoom out one more spot here so that I know the print's getting a little small there. But if you look at this formula for the multivariable linear approximation, and then if you look at this formula for the single variable linear approximation, notice how strongly they look alike. I mean, we've got the value of the function at whatever point you're doing your approximation, and then there's, at the end, there's a multiplication by x minus a. It's a dot multiplication, right, with the vector x minus a in the new formula, but anyway, it's analogous, right? And that suggests, right, these two connections suggest that there must be a strong relationship then between this gradient and our single variable derivative. And so I think this is a really interesting, like I say, it's at the moment just an eyebrow raiser, but the gradient that we just defined as a sort of a notational convenience, it's playing very strongly analogously the same role as the derivative did in the above formula. So I would propose that on the basis of that, and we're going to see more, that this thing, the gradient, maybe this is what we should be thinking of as the multivariable analog of a derivative. After all, it plays the role of the derivative in this linear approximation formula. So you see why, again, partial derivatives, they're nice. Right? They're very useful, they're very convenient to compute, they're indispensable as a computational tool, but is a partial derivative alone, a single partial derivative, the derivative? No, but this could be. Right? So this is really a more sophisticated, complete answer to that question. Did I see a hand somewhere? No. Okay. All right. Okay. All right, let's do an example. So here's a function, here's a point. Let's do a linear approximation of this function at that point. And notice all I'm going to do, I'm going to plug straight into this formula. And I just have to compute the various parts of it. So let's see here, f of a, I'm going to need to compute the value of the function. All right, well that's just, you plug in this point into that function and out comes 5. So no big deal there. So f of a is 5. Now I'm going to have to compute the gradient. The gradient is made up of all the partials. So I'm going to have to take the partials of that function. And y'all know how to take partials. Here they are. I'm further going to have to evaluate at the point A. Right? So really it's these values that I get when I'm plugging in at the point A, and so the gradient is 2, 4. Everybody's happy? And then of course x minus a, the vector x minus a, well you can see that in these coordinates here. Let's see here, I'll color code it. There's x. X has coordinates x comma y. And the point A, there it is. A is 1, 2. And so you can see what I have here. X minus 1, y minus 2. That's really just the coordinates of the vector x minus a. So, nothing to it. And then, if you wanted to, and it's not at all clear that this is advantageous, if you wanted to kind of multiply that out, fine, you could rewrite it like this. I think a case could be made that, very often this is the one that's computationally more useful, like especially if x minus a is a really small vector, knowing that your answer is going to be really close to 5. It's pretty handy to have that written there, right? It's a lot harder to see that that's the case in this formula. So don't feel the need to multiply stuff out. If on an exam I ask you to, find the linear approximation, you're very welcome to stop right there. Okay. Unless something in the question says otherwise. Okay. Now, here's another notational convenience. And by the way, don't forget, we wrote down this formula for the gradient as a notational convenience. Right? Here I'm just kind of preempting the notational convenience as it turns out. So this is going to be a notational convenience. I'm going to define this thing called DF. And you see here it's a matrix. Right? This is what we call the derivative matrix of a multivariable, vector valued now, no longer real valued, vector valued multivariable function. Okay, alright, so you can see that this matrix is made up of a bunch of partial derivatives, and there is a pattern to those partial derivatives. It's very important that you follow the right pattern. This is not just a set of partial derivatives that I've kind of tossed into a box randomly, right? They have to be arranged in exactly the right order. Notice that in this first column, all of the partials are with respect to x1. So this is what I will sometimes call the x1 column of this matrix, because that's where all of the partials with respect to x1 show up. And likewise, second column is the x2 column, et cetera, et cetera. And you can see right here that the last column, the nth column, is the xn column, because all the partials are with respect to xn. Everybody see that? That's a critical part of the pattern defining this matrix. Then also, there's a pattern with the rows. Notice in my first row, we're taking the partials of f1. Always partials of f1 in that first row. So I'm going to call this the f1 row for obvious reasons. Okay, and then ditto. This is the f2 row and f3 row, et cetera, and this is the fm row. M being the last output variable, because there are m output variables. Okay, how we doing? Is everybody happy? All right. Okay, so this thing set up in exactly this way with all this, pattern being respected. I'm just going to claim and leave it as an exercise for y'all to confirm. This is a good exercise. This is good mathematical weightlifting. I hope you'll do this. This is the linear approximation of that vector valued multivariable function. So in particular, this function has the same value as f at the point A, and it has all of the same partials, no matter which input variable you're taking the partials of, and no matter which output variable you're taking the partials with respect to. Did I say that backwards? I said that backwards. Shoot. No matter, let me do that again. No matter which output variable you're taking the partials of, right? Li is an output variable. And no matter which input variables you're taking the partial with respect to. There we go. Everybody good? Okay. So again, very healthy exercise. Please do this. How about this? Do it for like 3x3 matrices. Something like that, where you can actually write down. Once you get the dot, you get a bunch of different subscripts, and it gets a little confusing and annoying. But just check it for all 3x3 matrices, where your outputs are f1, f2, f3. Your inputs are x1, x2, x3. Check all 9 of the partial derivatives. A lot of good news happens. You're going to have a lot of, just like we had here, a lot of stuff that is intrinsically constant. And then for the purposes of taking partial derivatives, a lot of stuff that is constant at least while taking the partials, and noting how many constants you have. It's just all going to fall into place, and I think you won't have any problem. But good to flesh that all out and see, take it apart and see what it looks like. Good exercise. Okay. All right. So, again, quick application. Claim that this is our formula for linear approximations for these kinds of functions. Note here I have a function that has 2 inputs and 3 outputs. Now, because there are 2 inputs, we're going to be taking partials with respect to 2 inputs, and so we have 2 columns. Right? And because we have 3 outputs, we're going to be taking partials of those 3 outputs, each with respect to the previously noted 2 inputs. So we have ourselves a matrix of this shape right here. Right, so that's 3 rows, 2 columns. So this 3 by 2 matrix. Okay. All right. Partials are easy to compute. Good exercise. Again, make sure you can compute all these partials. And don't forget, our formula here requires that we evaluate the partials at the given point. So I got to plug that point A in, right? And then as a result, the actual computed derivative matrix to put in that spot in our formula is made up of these numbers right here. A little bit of arithmetic. So we're basically done at this point. There's our derivative matrix. Sure, I suppose we do have to also compute a couple other things. I do have to actually take this point, plug it in, see what the function turns into. This is my, that's my f of a. Yeah, of course. Right. And likewise, I've got to, have my x minus a vector, and again, there's x. And here is A. So a couple of details, right? But most of the work is the computation of the derivative matrix that we just talked about. How we doing? Now again, you could multiply this out. I don't really see the point in most cases. I guess if you were going to code this into a computer and you wanted to streamline it as much as possible, yeah, sure, multiply it out. Right? In most applications, though, you probably just leave it like this. Okay. All right. So everybody's happy. Is that right? Everybody's good? Okay. All right. We've kind of already made these observations, but let me go ahead and say it. This first column is all the partials with respect to x1. If you think about it, that means it is the partial of the vector-valued function f with all of its components with respect to x1, because of course that's what that partial derivative of a vector-valued function would be. Similarly, the first row is all of the partials of f1 with respect to all the different input variables, and that's our very definition of a gradient vector. So it's a neat fact to observe if you have a vector-valued multivariable function and you know its derivative matrix. If your derivative matrix is known, the rows, you can just read off those rows. Those are the gradients of the individual coordinates of f. It's pretty handy, for example. Okay, and I also already talked about that. Linear approximations, oddly, are not linear; they're just affine. But this thing, the derivative matrix, it's a matrix. It is linear, and thus the name linear approximation. Okay. All right. So moving along. I want to clean up a possible misunderstanding from single variable calculus about tangent planes. A lot of people think, and again, this is just kind of a sloppiness of language. A lot of people conflate the linear approximation with the tangent line. Like the tangent line and the linear approximation are the same thing. Well, not quite. The tangent line is the graph. Again, this very specific and arbitrary and no longer to be assumed or taken for granted, right? But this arbitrary construction called the graph construction. And yes, the tangent line is the graph of the linear approximation, which you can compute with that formula. Sure, yeah, right. But they're not the same thing. The one is the graph of the other. So, I know it's sort of fussy, but it's an important distinction. And so, likewise with tangent planes, right? We have this formula for our linear approximation that we just wrote down for, now that we're back to real valued functions here, so we can have a hope of being able to draw the picture, right? But there's our linear approximation formula, and the tangent plane is the graph. It's what you get when you set that equal to z arbitrarily And again, not to be assumed, right? But if you choose to set your linear approximation equal to z and then draw the resulting picture, then yeah, that graph is what we call the tangent plane. Everybody good? All right. Okay. So now we're going to get to talking about, but is it really a good linear approximation? I mean, I wrote down the formula. I think it's very plausible that as long as nothing goes wrong, that formula that we wrote down really does make sense and it really ought to work. But we can't just sort of hope and assume that, stuff's going to work out and nothing weird's going to happen. So I want to recognize that sometimes it does not work well. So let's take this function right here, for example. Now this is a admittedly weird function. But it's a function, and so we can very reasonably talk about it. We're going to define the function as follows for these values of the inputs x and y. In other words, if either x or y is equal to 0, then the value of the function is 1. So we get values of 1 above the x-axis, and likewise we get values of 1 above the y-axis. But anywhere else, the value of the function is 0. So the value of the function is 0 off of the axes, and so over there and back here, value of the function all 0. Everybody see what I'm talking about there? It's a very weird function, yes.
So it means that extends through the z-axis.
I'm sorry, one more time?
Does that x sort of extend through the z-axis?
No, I'm not sure what you mean by that. So the x-axis is this whole thing. Well, let me make better color choices here. Here's the x-axis. Here's the y-axis. Between the two of them, they kind of make up, if you will, our domain, representing all the inputs. So I guess I didn't understand your question. Say again.
So if we're plotting on 3 dimensions.
Yeah, that's right. So I'm making a graph.
Okay.
This is a graph. I guess I should have said that. But this is a graph, so I'm taking the values, the output values here, and I'm making that the vertical. Yeah.
Oh, I see.
Yeah.
I see. Oh, and then you're plotting that's 1 and everywhere else is 0.
Yes, that's right. Is everybody cool? Okay. All right. So so let's entertain the question of how we would do the linear approximation of this function at the origin. So we're going to look at x and y both equal to 0, and at that point, the value of the function is 1, no problem. If I were to take the partial derivative in the x direction, let's see, what is the partial derivative in the x direction? Well, I need to look at how the values of the function change as I start moving in exactly the x direction. And you can see right here on the picture, the values of the function, they don't change at all as I move in the x direction. It's constant. They just keep being 1 right along in there. So the partial in the x direction is 0. And likewise, the partial in the y direction. Right? So the value starts at 1 and then it keeps staying 1. And so that partial derivative, also 0. There's no problem with defining those partial derivatives at the origin. And so, if I were to just kind of blindly use the formula on the previous page, I've got a perfectly good first term, the value of the function. I've got a perfectly good gradient, and I could combine them per the usual formula, and I would seemingly then conclude that this is my tangent plane. But I think we can all agree that that is a horrible estimate of the function, because extremely close to the origin, the value of the function's way down here at 0. This is not a good estimate of this function. Everybody see what I mean? This is a bad candidate for calling a linear approximation. So, okay, how are we going to deal with this kind of nonsense? How are we going to exclude? What criteria can we write down that will help us just to say that no, we're not we're not talking about linear approximations for functions like this. So here's one thing you could do. You can look at this thing called the error. This will be our first attempt. We're going to look at the error, namely, what's the actual value of the function minus what is our estimate of the value of the function. And, actual minus estimate would be how far you're off, how far your estimate is off, thus error. And this does a nice job of excluding this function because the linear estimate, let's suppose as I approach the origin from that direction, let's say, the linear estimates of the values of the function are all 1. The actual values are all 0. And so my error just stays 1. And does this error approach 0? No, this is clearly a bad linear approximation. The error does not approach 0. So, good for this. It has successfully identified that this is a bad case for talking about linear approximations, and that's nice. Here's the problem. It does not do a good job in other cases. So here's another case where this rule of just make sure your error goes to 0. Bad choice. So here we go. Here's a function. Again, I'm drawing graphs, single variable even, to keep it convenient. There's a perfectly good function. And now let's suppose someone shows up and say, hey, I think this should be considered a good candidate for a linear approximation for this function. What do we think of this as a candidate for being a linear approximation? So just from an intuition standpoint, it's not even close. Right? It's pointing the wrong direction. It's clearly not a good linear approximation. And yet, from the vanishing error point of view, does the error approach 0? Well, yes, it does, because the error, the difference there, elbows, the difference between the actual value and our estimated value, that difference does approach 0 as you get closer and closer to the origin. So, not good enough. Right, this idea of is as long as the error approaches 0, unacceptable. All right, so here's a refinement of that idea, and this is the idea of what we call relative error. Relative error, it's not just error or how far off is your estimate. It's how far off divided by how far away are you from the approximating point. Magnitudes, of course. So they would call it relative error because of this idea that we're seeing, how big is the error compared to how far away we are in the input. Okay, so it's a new object to think about. Let's play with it and let's see how well this serves to refute this obvious failure. Right? I mean, again, I hope it's clear that this function 5x is just not well approximated by 3x. Well, of course it's not. It's clearly wrong. So, does our new criterion refute this candidate? All right. Well, let's see here. Here's my errors. My errors are that right there. It's 5x minus 3x. That error does approach 0, but again, that's not the game we're playing anymore. We want to look at error divided by how far away are we in the input. How far is the point X where we're looking away from the point A where we're doing the approximation. And that is X minus A, otherwise known as X in this case, because we're approximating at the origin. And you look at this relative error then, and this relative error is just 2. It does not approach 0. So the relative error did not vanish. And if our criteria is that, not only error, but relative error needs to vanish, then this candidate linear approximation is refuted. It did not satisfy the requirement of vanishing relative error. So this is a good criterion. Correction, this is a better criterion than we had before. Right? This idea of looking at the error by itself, that just doesn't work. Relative error does. So this is going to be our definition, and there's, of course, much more sophisticated things that arguably really should be said, but this is the big idea behind this definition I'm going to make here for what it means for a function to be differentiable, and for our familiar formula from the last few pages to be the linear approximation. And we use these terms interchangeably. What it means is that the relative error approaches zero. And that's what we used above, and we were happy with. Relative error approaches zero. Now don't forget relative error is this formula. Don't forget that error is this formula. And further, don't forget, and now I'm going to throw some parentheses in here just to make this a little bit easier to look at. I'm going to kind of group together these terms, and don't forget that means you have to distribute a minus. Don't forget that this L, our linear approximation, is this great big thing here. Everybody with me? So we end up with kind of a mouthful here. This is a great big thing, and I need this great big monstrosity to approach zero as x approaches a. And if so, then the function is differentiable. And our usual formula is a perfectly reasonable linear approximation. Okay. All right. And bad news, very bad news. This is super inconvenient to deal with. In fact, that's just the tip of the iceberg. We also have to deal with it in the sense of taking a multivariable limit. And you may recall we kind of skipped that section in this book. So we not only is it hard to deal with, but this is something we're not even prepared to deal with. Good news, we're going to have a nice workaround that we'll get to momentarily. But anyway, in terms of intuition, this is where the definition comes from. One last little clarification. We usually think of this as noted here as actual value minus estimated value. Sure, actual minus estimated value, fine. But notice you can group these differently. I could group these terms like this. This is how much the function actually changed. And this is our linear estimate of that change. So, you can think of it as actual value minus estimated value, or you can think of it as actual change minus estimated change. Just for as a language point, we do use words to describe these. The actual change in the function we call the increment. It's a pretty natural term. You probably heard that used in everyday life, some here and there. And our linear estimate of the change is called the differential. And y'all have seen this notation before, I'm sure. DF is just our linear estimate of how much the function changed. How are we doing? Everybody on board? Questions? Feel free. Everybody's good. Okay. So here's some really good news. Again, that great big multivariable limit is a bear to deal with. So good news, there is a very convenient, closely related idea that will answer that question for us. It's called continuous differentiability. It just means, as it turns out, you just look at all the partial derivatives, make sure they exist, make sure that they're continuous. Their being continuous turns out to be a tremendously powerful fact. That the partial, not the function, that the partial derivatives are continuous. tremendously powerful. And if this is the case, if your function is continuously differentiable, then it is differentiable. That bear of a limit on the previous page, you don't have to mess with it. You immediately know as a result of this argument that the function's differentiable. And all you got to do, right, it's an easy little test. All you got to do to be able to use this argument is check for continuous differentiability. Namely, you just got to compute the partials, make sure they exist, make sure there's no divide by zero, right? And then further check that they're continuous. And most of the time, that's just, well, of course it is, it's a polynomial, or, well, of course it is, it's an exponential. Or, of course, there's large, huge categories of functions that y'all already know are continuous. So here is a quick application then. Here's a function. Is this differentiable? Do we have to deal with that bear of a limit on the other page? No. Much easier. We take the partial derivatives. They're all polynomials. We know that polynomials are always continuous. Well, that means that our function is continuously differentiable, and then by this theorem here, that means our function is differentiable, and so yes, answer to this question. Oh, I'm sorry, I lost track of time. Just went over. Okay, so we'll draw the line right there. Y'all have a good day. See you on Friday, where I guess we also have homework due on Friday. Always keep an eye on the lecture schedule. I'm sure y'all are getting in the groove on that. See you later.